find some A psi here to certain non-Kähler elliptic surfaces. So certain non-Kähler surfaces, as in the title. So just to be concrete, what we're looking for is for such a surface S, we want some correspondence between coherent analytic sheaves on S, and so Lagrangians in some appropriate Fukaya category. And for me, okay, so first of all, I should say I need to use analytic sheaves because some of these spaces will not have algebraic structures. And I'll actually get all of my coherent analytic sheaves as holomorphic vector bundles. So if you want, you can just think about holomorphic vector bundles. Of course, okay, and then I should say these surfaces will also be compact in this talk. So of course, if one of them is algebraic, by Gaga, you know that the coherent analytic sheaves are going to be the same thing as the algebraic ones. So you'll recover kind of standard mirror symmetry. So the first thing I should talk about is logarithmic transformation. So that's the only time I'll write it out in this entire talk. Normally I'll say just log transform or just LT. But what is this? So this is some.
So S is a K3 surface?
Sorry?
Is S a K3?
No.
I'll tell you what S will be. No, I mean I will not treat K3s. Yeah, so this is some operation on elliptic surfaces. So what it does is, so if you have some surface S over B and a point B and B, so that you should have a smooth fiber over B, you can do some log transform. And this is going to have parameters AB. So this is a vector in Z2. So a pair of integers. So it's primitive in Z2. And then A is greater than 0 for this stuff. So okay, you take an elliptic surface. So you do a log transform at B. And then you get a new surface S prime over B. And then the result is, so away from the fiber over B, you have a biholomorphism. And then in this respects the elliptic vibration. So really away from this fiber, it's the same complex surface. And then S, so this S prime has a multiple, or has fiber with multiplicity A over B. So you take an elliptic surface and then you produce some other elliptic surface, and then this one has a multiple fiber. So it's important to note that this is not a birational move. So it changes, e.g. like algebraicity. I'm going to be using that. It can change the Dyer dimension. Potentially. So you're really getting at some new surface. And so the hope is that given mere so given a mirror to S, so if we have some surface that we understand mirror symmetry for, we hope that we can find a mirror to S prime. So given a mirror to S, okay, so there's some motivation for doing this. I mean, I guess first of all, you would want to just kind of expand the zoo of things you know HMS for. But in particular, people have been interested in, so of interest, people care about the mirror to the Dolgachiev surfaces. So X. So I'm going to denote this X2 comma Q, and then this is equal to some rational elliptic surface with two log transforms, a multiplicity Q and Q. So these things come up, for example, if you're studying exotic four manifolds. So these things are all homeomorphic, but not diffeomorphic as soon as you're on equal Q. And another feature is that they have maybe interesting behavior in their derived categories. So at this point, I should say, okay, outline of the talk. So this was all sort of the preface. The first half will be on mirror symmetry. Will sort of be like from my thesis. So this is mirror symmetry for P1 times E. So like a very stupid, elliptic surface. And then in the second half of the talk, it'll be much more speculative. And I'll sketch a mirror construction. I'll hopefully sketch a mirror construction to these Dolgachiev surfaces, X2 comma Q. But yeah, so that will be very speculative. So the talk will go off the rails at some point into the land of speculation. But I think the first part will consist of some true statements. So
may I just ask you, what is the meaning of this parameter B?
Yeah, so this is sort of what you twist by. I mean, it's you're going to kind of take your elliptic curve and then kind of glue it back by some translation by one of the like A torsion points, and then B just tells you like which one essentially. Okay, so yeah, so section 1. So HMS, I'll just say for the Hopf surface. And friends. So just fixed notation. So let A is always going to be a pair, A naught, B naught, A infinity, B infinity. If you've seen me give this talk before, you'll be very happy to know I've changed the notation to this new notation, which is, I think, a little bit more sensible, but it means I'm a little bit less fluent in it, so I apologize if I like screw up some notation. If something doesn't make sense, just tell me. But okay, so this is, so these are pairs of integers, two pairs of integers, and they're primitive, and have these first ones not equal to 0, so you can do log transforms with these parameters. And then so let's let A naught is going to be equal to the pair 1, 0, 1, 1. And I should note that doing a log transform from their 1, 0 is trivial. So topologically, like what this thing is going to do is some sort of surgery where you move a neighborhood of the fiber, glue it back in. The 1, 0 case will be you're just gluing it back in by the identity on the boundary. Sorry. So then S of A naught. So the reason I'm defining this is that this is a surface you might know. So this is the Hopf surface. So it's C squared minus 0, quotiented by the relation Z is identified with QZ. Oh, sorry. So let me leave this on the board. So this is S sub q. But as you might have guessed, I have another description of this in terms of log transforms. So S of A is going to be surface obtained by performing log transforms of parameters A naught, B naught, A infinity, B infinity, to P1 times EQ. So EQ is going to be the elliptic curve with modular parameter Q. So this is C star mod C QZ. So you perform log transform of these parameters to B1 times EQ over 0, infinity, respectively. Yeah, and then I claim that if you do it with these parameters, what you actually get is this Hopf surface. So this thing I should note is diffeomorphic to S1 times S3. So in particular, it's not algebraic, it's not Kähler, it doesn't have any H2, so you don't have anywhere for symplectic form to live, Kähler form to live. Okay, but yeah. So what can we say about like sort of the complex geometry of this Hopf surface? So we know it has a map to P1 by construction. So S of A naught maps to P1, and then this is just given in coordinates by Z1, Z2, maps to Z1 over Z2. And we can we can trivialize this over the two copies of C that you get. So we can trivialize this vibration away from one fiber. And if you do this twice, what you obtain is that S, the Hopf surface, is equal to two copies of C times E, EQ, glued over a C star times E. So yeah, whenever I write E, it means this E sub Q. And whenever, I should have a Q here too, but I'll drop it. Okay, so now you might say, okay, I don't have any idea how to do homological mirror symmetry for this Hopf surface, but I do note that I can do homological mirror symmetry for C times E. Those are two spaces that we understand HMS like very well for. So what one can then do is say, okay, I want to express any sort of coherent analytic sheaf on this Hopf surface via this cover by these two copies of C times E. Okay, so now, yeah, I apologize, this is going to be a smaller board. But so, strategy. We have maps from coherent. Okay, and I'm going to write co, but this always means coherent analytic shapes. So we have maps from co of S of A naught to coherent shapes on C times E. Times E, these two pieces by restriction. And then we also have maps restrictions to this. Well, okay, let me write it like this. So then we further have maps to C star times E, again by restriction. And then the map, kind of gluing the two sheets together, is induced by the transition maps from these two copies of C times E, which you can figure out is ZT maps to Z inverse, Z inverse. So this is not an algebraic map. It might look like it, but it's because I've written the elliptic curve multiplicatively. Sorry. Yeah, so you have this diagram of coherent sheaves on your Hopf surface. You want to match up, so you want to match with some diagram of Fukaya categories, so now I'm really going to be cramped. But you have some, thing Fukaya category here. So I'll just denote f of a naught, which should have maps. Let me write this like this, because actually, this is all superposition, so that maps like that. So this has maps to some wrapped Fukaya category, or like, what is the mirror to C times E? Well, it's going to be the mirror to C times the mirror to E. So mirror to E is just some T2. Mirror to C is C star with one stop, maybe. So I'm going to call, so I'm going to call Y is equal to, I'm going to write it like this, R times S1 times S1 times S1. But of course, this is the SYZ mirror to C star times E, C times E, with the symplectic form that you get. So if you choose coordinates correctly, this is going to be dt, which dt, which d phi t, plus ds, which d phi s. Yeah, okay, so then now we have the maps of the wrapped Fukaya categories here. So this is y, again with some stop, which I'll write as 1 times t2. This is some wrapped Fukaya category y with, again, some stop, 1 times t2. I'm thinking of the stops as some hypersurface in the boundary at infinity, so that's where I'm going to make 1. And then, you know what, this is really terrible to do this all on one board. So I'm sorry to make you look at 2 boards at once, but I'm going to do it just over here. Just because I want to keep the boards adjacent. This thing is bigger, so we have some diagram categories. F of A naught to some wrapped Fukaya category of Y, 1 times T2. Again, wrapped category Y, 1 times T2. So this maps by acceleration, stop removal, what you want, just to the wrapped Fukaya category of Y. Same thing here. And then you want some automorphism of this category, which sort of respects this automorphism here. So the naive thing to do is just kind of write down sort of the logarithmic version of this automorphism. So let me just write this. So this is going to be induced by Ts maps to negative T, S minus T. So what I mean is this is just some map on the base coordinates T and S, and then you get a symplectomorphism of the space Y. Okay, so note, so you need a model of WY, call this map, I don't know, F, with F, which accommodates F as an automorphism. The standard one will not do it. So, yeah, and then I have more to say about that, but you really need to sort of enlarge your wrapped Fukaya category. Previously, we were just kind of considering maybe cylindrical Lagrangians or something, and now you need to kind of allow them to have different sort of behavior at infinity. And if you kind of like go through this whole story, let me erase this here. So upshot is that you can think of Lagrangians in here as a sort of fibering over this real axis times T2, similarly here. But if you think about how this F is going to act, it's not going to sort of preserve that real axis condition. You're going to get sort of linear boundary conditions at each end, but sort of mismatched ones. So the upshot is you need to define a Fukaya category with varying boundary conditions on the ends. Not two ends. Okay. Before I move on, I want to say, like, there's a similar sort of diagram for each of the surfaces I consider. You're not just going to have this like C times E here. You're instead going to have something that has a multiple fiber. But this diagram, I'm showing you it because I think it does sort of help clarify how you're sort of gluing together, or you're sort of considering sort of compactification. The log transform tells you how to compactify both ends of C star times E, and then you're going to have some sort of diagram relating sheaves on sort of the two partial compactifications. Right. So now I'm going to define a Fukaya category for any matrix, or for any of these pairs, A naught, or A1, A naught, U naught, A infinity, B infinity. So define. So f of A is equal to, so the objects are going to be, let's say, nice Lagrangians in Y, plus extra data, things to make your floor theory well defined. That's what nice means. Plus extra data, plus local systems. But I won't get into details today. But so nice Lagrangians L, such that A naught phi t plus B naught phi s. This function vanishes identically on L intersect, say like t much less than 0, and then A infinity phi t plus B infinity phi s is equal to 0 on L intersect the other end, so t much greater than 0. So if I draw a picture, so here's a picture of Y. So this is my T phi t cylinder. And then I'm just going to say it's times T2, so this is the S phi S 2. What's happening is I sort of, okay, and then say I have some Lagrangian sort of living in this space. So, okay, I'll draw it as like some product Lagrangian, but it need not be a product Lagrangian. You know, at infinity, it's going to sort of project over one sort of loop. Well, this is a more interesting loop. over one sort of loop in your T2. So this is a phi T, phi S projection. And at the other end, you have some other loop that it's going to fiber over. So maybe it just like goes like that. So again, yeah. So this is the projection of L sort of sufficiently far out. You calculate the Homs. Okay, so now I want to say is, well, okay. Let me just tell you how to calculate Homs. So the Homs, so they're calculated through with some localization procedure. As for, you know, so they're calculating some localization procedure, like as in, for example, like Ganache, and Shinde, or other work, following ideas of Abigail and Seidel. But the upshot is that there's a quasi-isomorphism from the Homs of some L and K objects in the Fukaya category to the Floer complex of size of H. So some Hamiltonian perturbation of L with K, and then H, right here. So H is some Hamiltonian which equals epsilon times absolute value of T for T much, much greater than 0. So what's happening in this picture is this Hamiltonian, which is like equal to some absolute value of T, is just going to kind of push off in the T direction. So at one end, like if this is L, you might see that like this is, this would be like a H of L. So incidentally, all of what I'm, nothing, like this is sort of not a new idea at all. I mean, obviously this is just kind of putting stops on both ends of this Y. So, so this whole thing can be phrased in terms of stops. Okay, so. Yeah.
I probably misunderstood. So you're saying that we can set up to actually disjoin this Lagrangian from itself in the fiber?
Sorry, 1 second.
No, this is a Lagrangian.
This is a Lagrangian projection. This is literally just like at the ends you're just pushing off, so you just ensure disjointness away from the compact set. Yeah, I should note that. So yeah, so this is disjoint. Yeah, thank you. So this is disjoint outside of compact set. Okay. So theorem. So the only theorem I write today. Theorem. So functors. I'm realizing now I didn't tell you how to compute differentials and so on. So let me write the theorem and then I'll say a few words. But so, okay, so they're full and faithful functors from the Picard group, the analytic Picard group of S of A to the zeroth cohomology category of this Fukaya category for all A. Maybe I don't even write anything about how I'm going to compute these higher product, but you just do it as you would do it if you were working in some like wrapped Fukaya category with stops or like if you're working in some Fukaya category associated to a Landau-Ginzburg model. So you just need to sort of push off. You're going to count disks, and you just need to sort of have the boundaries of the disk be pushed off in the correct order. Okay, people are looking confused, so let me actually draw a picture.
Excuse me, what do you mean by peacock?
Yeah, so this is a subcategory. Okay, so this is just some category where the objects are, as in your objects are just the elements of your Picard group, and then the morphisms are just, I guess the way I've written it, like the morphisms are just given by X0 groups between two objects. I've written this with an H0, I could do the full cohomology category, and then you would have some equivalences. For any two pairs of objects, you would have some equivalence between X, sort of the full X ring, and the cohomology ring here. Or the H, cohomology ring there.
So this is just boundary between walls and walls?
Between these, so this, like the Picard group is a category with this, yeah. And this is the zeroth cohomology of the Fukaya category. So the objects are just your objects. Yeah. Okay. Okay. I won't put it on the board, but if you kind of remember the diagram of categories I had previously, I also have, I can fit these equivalences into sort of some diagram of equivalences that matches up pieces of the diagram which express the sheaves on the surface in terms of this cover. But I'll spare you from that for this talk. Okay, so other questions? Okay. So in general, or let me just say fact. This analytic Picard group is equal to Homs. You can express any line bundle on your surface S sub A in the following way. So you have an equivalence between this Picard group and the Homs of the fundamental group of your surface SA to C star. So what you can do is you can prove that any holomorphic line bundle on this SA pulls back to a trivial bundle on the universal cover, which in all of these cases will be, or rather like whenever your surface is non-algebraic. Okay, sorry, so when SA is not algebraic, this is also a condition here for all A, such that SA is not algebraic. And I actually, I want to correct, sorry, I want to correct the sign error here. This is a minus sign. Okay, so e.g., so how does this work for the Hopf surface? So the analytic Picard group, the Hopf surface, so again this SA naught, is equal to C star, because recall that this thing is just S1 times S3, and the map here, like, so if you take lambda and C star, you get some line bundle which I'll denote L of lambda, and the total space of L of lambda is equal to C star, or C squared minus 0, times C, and then you quotient by ZT, identified with QZ, that's the quotient on your C squared minus 0, lambda T. So you just kind of pick a scaling factor for your quotient. Okay, and a fact. So now I'm going to show you how this theorem works in the example when this SA is this Hopf surface. So in the example when A is equal to A naught. So I will show mirrors to these line bundles. So.
So can you say again what are all these A's in this theorem?
Yeah. So A recall is some pair of integers A naught, B naught, A infinity, B infinity, and these are the parameters you use for your log transforms. So S of A is P1 times E with 2 log transforms with these parameters. Yeah.
So do you think this still holds when SA is algebraic?
Yes, it does. But I don't have it written. I mean, it does, but we already know that. So what's happening when SA is algebraic is you're actually just kind of doing 2 log transforms with the. You can kind of do the log transforms so that the total space is just going to be defined as some quotient of P1 times E by some finite group. So this is algebraic. Then you have a story of mirror symmetry, say for like weighted projective spaces times E. And if you trace out that story, it would replicate what you get in this case. Yeah. So I should say, like for example, like when A is equal to 1, 0, 1, 0, so the trivial case. Well, now I've erased my boundary conditions, but the boundary conditions are just going to be like phi t is equal to 0 on both sides. And that's the exact sort of that's the same condition as it would be like if you have some Lagrange, it should fiber over the real axis under the Landau-Ginzburg map to. I mean, your mirror in that case is going to be the product of the mirror to P1 and the product of E. So this is going to be some Landau-Ginzburg model, and I claim that should be some relation. The objects of this Fukaya category should also be objects of that Landau-Ginzburg model. I'm happy to do that in detail at the end, but I want to write down this equivalence before too late. So, or I want to write down, like, show you how this works out. So in fact, so if you compute the cohomology of these line bundles on just the Hopf surface, so S of A naught, this is going to be equal to 0 if lambda is not equal to q to the n for some q, or sorry, for some n.
In Z, you mean?
Thank you. Yes, thank you. Is going to be equal to the cohomology of O of n tensor with, quickest way to write it is cohomology of S1 for lambda is equal to q to the n and Z. And in this case, actually, L of q to the n is equal to the pullback of O of n from the elliptic vibration, so pi, so you have S of A naught. Say maps to P1. So you expect, so in particular, you expect to have sections if the line model you're pulling back has sections. Yeah. Okay, and then I should say that this, I mean, in this case, this is obvious, but in this case, this is equal to the line model corresponding to the divisor n times f. F is your fiberglass. So, where did my eraser go? So for lambda is equal to just say q to the k. Now k does not have to be an integer, but k is in R. Phi of Lk, so the image under this mere functor, so phi of Lqk is going to be equal to the Lagrangian section, so the Lagrangian, which I'll write in this way, Ts, so this is some parameterization of some Lagrangian section of your SYZ fibration, negative k. Rho of t here is just a map from R to 0, 1, increasing, so this is rho of t. So just something that interpolates between 0 and 1. And then we can, so when we can verify when Q is not in Z, that, so let's call this thing L, Roman L sub K, LK intersect L0, so this should be near to the should be mirror to O, is equal to the empty set. Why is this? Because this parameter here, this negative k parameter, is not an integer. So if you project this, so this is some product Lagrangian in C star times T2, this is the T2 factor here, and it's just going to be disjoint in that factor. For the other ones, so if k is an integer, well, let me just do the case when, let's calculate, so let's calculate f of some perturbation of L0, Lk. Let me just do the picture for k equals like 2. So the projection, so this is going to be pi to the phi pt plane, so this is universal cover, of L0, so this is going to be in black, or rather, lifts of L0 to the universal cover, and then in blue, I'll write the other one. Oh, sorry. So H of L0. And then in blue, I'll do pi, again, some projection to the T phi T plane of a lift of L2. So this thing, so it starts out at 0, and then it kind of varies in this plane for a while. So this is, yeah, so this is the t coordinate. This is the phi t coordinate. And then what is the other? Let me get straight from my notes. There's like, okay, so then this perturbed guy is gonna look like this. So again, we're kind of pushing off in the positive direction here, pushing off in this direction over here. Okay. So the upshot is that there are 3 key values of intersection. So I don't really know why I'm doing this. I mean, this is just mere symmetry, by which I mean like this is just going to be some copy of mere symmetry for P1, right? In this T phi T vector, okay. So there are 3 T values of intersection, and then you get an S1 of intersections there. Because remember that these, this L2 thing is going to be, okay, so I should say this is a lift of L2. But this L2 thing is some product Lagrangian, and in the S phi S factor, it's just going to be identically equal to the 0 section. So every time you have one of these T values of intersection, you actually have a whole S1 worth of points of intersection. And then if you kind of do a small perturbation, you're just going to pick up a copy of the cohomology of S1 in your flow complex. So so then by thinking about, okay, what's happening for positive integers, for negative integers, gradings, so on, you can conclude, that your flow complex of these guys, 0, K, or Ln, say, well, okay, LK, is going to be equal to this cohomology. You wanted P1, okay, and then tensor with the cohomology of S1. Okay, so one thing I want to also show you how this works in the well, okay, so I want to first note this is delta phi t is equal to K, and recall that this thing was in this setting K times the fiber. More generally, say for SA, now I'm going to write some complicated thing. So the projection, so the mirror of your line bundles will still be product Lagrangians, and you have this thing that pi of t phi t. So the projection, similarly like the sort of projection of the some lift of the mirror to O of say n over A naught times F plus plus N2 over, or let's say N0 over A0 of F plus N infinity, A infinity of F. I'm just writing this to make the next thing clear. Take some lift of that. Will look like some sort of a similar story where it's just some sort of thing that interpolates between two values. And this total delta t, so this value will be negative n infinity, A infinity, and then this will be N0, A0. So what I'm trying to show you this picture, okay, and so, yeah, and then this delta phi will be this N0, A0 plus N infinity, A infinity. And what I'm trying to convince you with this picture is that this is really actually showing you like what's happening near each fiber. Like you want to think about this as sort of like your F over A naught is the singular fiber like with its reduced scheme structure, similarly for here. So you can just kind of build line bundles by taking copies of if you build a line bundle by taking using those divisor classes, then you can understand the mirrors pretty easily. Okay, so in my remaining 10 minutes, let me tell you about my ideas about other spaces, but hopefully they're plausible. Great, so the question is, log transform away from an anti-canonical divisor. Or just, log transform at general fibers. I sort of got lucky in that my fibers I'm doing the log transforms at are not showing up in my SYZ picture. So how do I do a log transform at, say, more fibers in P1 times E? So the idea is to use the model that we learned about this morning of Auroux, Efimov, Katzarkov, for LG models, incorporating singular Lagrangians. So I want to think of sort of doing, if I was doing log transforms over 3 fibers of P1 times E, what I could think about is sort of doing, as sort of like breaking these sort of fibers up using some sort of pair of pants like this, and then taking, sort of doing the mirror to the pair of pants construction that we learned about this morning. So the conjecture is that you draw this sort of picture. So this is your, union of 3 coordinate axes in C3 times, okay, and then you do times T2. So this is like mirror symmetry for this piece times mirror symmetry for that piece. And then you put some A1, B1 boundary conditions here, A0, B0 boundary conditions here, A infinity, B infinity boundary conditions here. I conjecture that this is mirror to the P1 times E, log transformed at P0, 1, and infinity with parameters AP, BP. So the objects of this Fukaya category, so need Fukaya category with appropriate objects. And what I want to say is that sort of you can put a symplectic form, the question is what to do with the singularity. Like, you know how to consider Lagrangians. Here you have these boundary conditions on each of these sort of ends. What Lagrangians do you allow? Like, how do you model the behavior near the singularity? And I don't want to get into that because I only have like 1 minute. But I think maybe like a thing that would work maybe is just say like, okay, these need to decompose as product Lagrangians in T2 and this sort of singular picture that these people are developing. Anyway, so this is conjecture. And then I want to say that, so part 1 is that this is mirror, and then part 2 is that like if I take something that sort of has some like delta phi t here is equal to N1 over A1, delta phi t here is equal to N0 over A0. So I'm taking like some product Lagrangian. So I'm taking, this picture is now not making any sense, but what I'm doing is I'm saying, like, say I have some Lagrangian which has some product structure, or which is some product Lagrangian in this and this. So that you can kind of figure out how much things twist, around here. In each of these legs. So phi t is equal to, say, n infinity over a infinity. And then you expect that this thing, and then, okay, times like just the 0 section in T2. So this Lagrangian L is going to be mirrored to O of n naught A1, A0, N1, A1, N infinity, A infinity of the fighter class. And I think one can get very easily from this AEK machinery some equivalents of Hom spaces in the same way that you would do for the non-singular guys. Okay, but in my very last 4 minutes, like, why would this be good? Well, this is good because
Sorry, what's the statement once again?
so the conjecture is that this is mirrored to this, and that this Lagrangian, this product Lagrangian, is mirror to this this line bundle. Yeah, and this is very natural from this perspective. Yeah. Okay, so that conjecture I think is maybe doable in finite time, assuming you have this AEK stuff. The following one I think maybe is not. But the conjecture is that, well, okay, so let me just say, like, we have some mirror correspondence between some Landau-Ginzburg model, so mirror to the rational elliptic surface, and what you hope. So this is some Landau-Ginzburg model with 9. So W maps from M to C with 9 singular fibers. And what you now hope is that you can kind of, to get your Dolgachov surfaces, like you're going to do some log transforms to this space, and you hope that you can kind of glue on this object to your mirror space, to your mirror space here. So then the conjecture, okay, so say M sub R is going to be equal to M, or is going to be equal to the preimage of sort of the complement of a disk of sufficiently large radius. So Z and C, Z is greater than and then this is symplectomorphic for sufficiently large R to some cylinder times T2. So what's happening is, like, you have some complicated, so M, it has some complicated behavior in some compact set, but then away from some compact set, it just decomposes symplectically as some cylinder times T2.
So how many log transforms will you do?
I'm going to do 2, but I haven't done them yet.
But if you do one, you should still get U1.
Yeah, so let me show you what I think is happening. So this thing, okay, and then this, so this MR is going to be this thing with a stop, right? So this stop is something like the real axis times T2. What I think you should be able to do is say something like, so here's a copy of M, so this is M minus MR, and then we have union this thing times T2, and then what I want to do is now, so I have some stop here, I want to attach it to one of these things where I have the correct stop there, and then add on two of these sort of things hanging off, with these stops of the form like 2, and 1, well, okay, R1, B1, and then Q, B2, and then I hope, so this is like dream. So I hope that this is mirror to this this Dolgachov surface x2 comma q. So the reason I imagine that doing just one log transform is not going to change the behavior is that I think what's going to happen is like what you might want to do instead is just sort of glue on only one, or sort of like what you hope is that if you just sort of have some, if q equals like 1, 0 here, so you're not doing any log transforms here, this leg can just sort of go away. Like you know, it's the same thing that like in this picture, you can just sort of not do a log transform here, and then the whole picture should reduce to just mirror symmetry for P1. And here similarly, I hope that if you don't do like this log transform, say, then this like kind of goes away, and all you're sort of doing is changing the stop from some element of some homology of this cylinder times T2 to some other element. But you hope that the symplectic geometry does not really feel what element of the homology it is. So I will stop there, but answer any questions.
So what you expect when you do logarithmic transform more than not just two, many times?
Yeah, I mean, I don't know. I mean, you could imagine you just start gluing, you know, taking something with many legs, but I mean, I don't know. You need to somehow keep track of the, like somehow like, there's some contradiction here, right? Which is like, if indeed just doing one doesn't change anything, well, then what's to stop you from just doing one and then doing another one? So then you would just sort of have some, like what you know is wrong is like you don't want to have sort of chains like this. So this is one stop here, and then like one stop there. I think, well, it's not clear. I mean, maybe this works, but I don't think this works. I think what you really need to do is kind of consider this kind of singular thing. But yeah, as I say, I don't know very much. Or anything.
Where is the fact that it becomes an elliptic surface recorded under this mirror?
Sorry?
I mean, you have something which is almost rational, almost found, and then it becomes a surface which is elliptic. It's not a general type, but it's elliptic. So where is this recorded under mirror symmetry?
I don't know. I haven't thought about it enough yet. But the hope is that you have sort of an explicit enough description of all of the objects that you would care about to sort of be able to trace out the behavior of, like the mirror to coherent shoes and so on.
Other questions?
Yeah.
How sensitive your mirror depends on Q. So
Yeah, I mean, it depends on Q. I mean, it's also gonna like, somehow I completely swept under the rug the rules for sort of propagating intersection, or propagating disks through the singular point too, right? And I imagine that those rules are gonna feel like sort of the location of the log transforms at. So there's a lot that this is ultimately gonna depend on.
but can I see some difference when Q is 3 and Q is 5 and Q is 2?
Well, I mean, you can see some difference topologically in the mirror to the Hopf surface. And you can see, like, for example, like if your surface has a fundamental group, like a fundamental group with torsion parting fundamental group, then that is reflected in the Fukaya category. So you have some.
Yes, so how do you see this, let's say, how do you see this in the mirror symmetry?
I don't know. I mean, very, very, very much in progress.